In the topics covered so far, we have mostly considered those steps in the mining process leading up to the actual mining operation. And although they are relevant in the broader context, they don't lie at the core of the mining engineering discipline. The art of engineering has two principal aspects. These are achieving an outcome and doing so in an optimised way, subject to a complex array of limitations and constraints. So with these ideas in mind, we can identify the core tasks of the mining engineer as being to produce a conceptual design of an operation to exploit a mineral deposit which is technically feasible, economically viable, environmentally responsible, and most importantly, fundamentally safe for miners. And to develop the conceptual design to produce an operational plan which achieves the above aims at every stage in the life of the mine, and to oversee the mining operation as it occurs and continuously refine the plan as circumstances and conditions change and problems arise. As with all engineering problems, there is no single unique way to design a mine. There are probably as many different ways to mine a mineral deposit as there are mining engineers. Solutions to this problem can generally be grouped into two categories: those that simply won't work, they're not technically feasible, and those that will work, but they may or may not be optimal. To develop a technically feasible mine design requires the application of a knowledge of science and engineering mechanics. One can envisage an amazing array of clever theoretical solutions to mine a mineral deposit, but assessment of their feasibility and practicality requires that every aspect of them be quantified in some way. There are many things to be decided, but they can generally be grouped into two categories. Will the geometric arrangement of the mine at any stage in its development be stable? And with the resources we have, people, tools, equipment, products, can we physically achieve that arrangement? To answer these questions, we need a quantified knowledge of applied science and engineering mechanics. Specifically, that knowledge should include an understanding of stress and strain, fundamental behaviour of rocks and discontinuities, stress distributions in the ground, and mechanisms of instability and failure. We have devoted Module 2 to a more detailed consideration of some of these issues, and the headings above serve as a list of the topics we will consider. Even after we have decided upon a physical arrangement for the mine, and we have decided how that physical arrangement should evolve as the mine develops, we are not yet in a position to start mining. There are many different paths to achieve an outcome. There are many tools we can use to break rock and excavate a hole. There are many ways to transport rock and ore. There are many options for managing waste. There are choices to be made about how we balance development activities with production and how we want to run the mine as a business to optimise the return. Key decisions that must be made include: should we use surface or underground mining methods? What methods will we use to break up the ore and waste rock to maximise effectiveness and minimise cost? What methods or machinery will we use to transport the ore and waste rock? How much ore are we willing to sacrifice if it allows us to use a more efficient excavation method? How do we manage mining and beneficiation wastes? What are our obligations in regard to mine closure and rehabilitation? And how do we manage safety? A large part of the role of a mining engineer is to determine how mines operate as their physical arrangement evolves. You'll see lots of examples of this in Modules 3 and 4.